And welcome students. We are now starting our lesson on I/O or input output. So programs so far that we've done up to this point have pretty much no really requirement for human input. Pretty much we just load up the program, enter in whatever values you want in the memory, and just say run, and it just does it. But what if we wanted to include the option for human input? Where does that data in turn come from? So this is how we get then into I/O, which is connecting the computer to the outside world. Because others are just it's self-contained. So the types of I/O devices typically are characterized by the following. Behavior, which is input, output, and storage. Input is typically things like a keyboard, motion detector, network interface. An output is usually limited to things like monitor, print work, network interface. Storage mediums, such as a disk or CD-ROM. And then also the data rate. So how fast can the data be transferred from one medium to another? For example, keyboard is about 100 bytes per second. Your disk is about 30 megabytes per second. Network is anywhere from like 1 megabyte to a gigabyte per second, depending upon like your card that's on board on your PC. Now, if we look at the I/O controller here, we have several different things going on. The first of which is the control status registers. This allows the CPU to tell the device what to do, which in case it's the write to control register. CPU then checks whether the task is done, which is a read status register. So you have a write and a read status. So if we look up here in our visual here, we have the CPU, and you can see there's a back and forth here for control status, which then control status can feed to electronics out to display, which is all part of the graphics control here. Now the data registers, the CPU transfers data to or from the device, and then the device electronics performs the actual operation. So it's like pixels on your screen, bits written to or from the disk, characters on your keyboard being generated. Now, from the programming side, because that's really what we're going to be looking at. With the interface here, we want to first ask how many device registers are identified. So how do I identify these? Typically, what you see, it will be memory mapped registers versus special instructions. Also, how is timing of transfer managed? Is it asynchronous or is it synchronous? In other words, is it going with the CPU or against it? Who controls that transfer of information? Is it the CPU, which is done through something called polling, or is it the device, which is something called interrupts? Let's look at a little bit of that memory map versus I/O instructions. So in here, the instructions designate opcodes for input/output. All right. And the register and operation then are encoded in the instruction. And that's what we're looking at here. So you can see here's the opcode for I/O, and then we have the device, and then the operation itself right here. And then of course, when we look at memory mapped, we assign a memory address to each device register. So in memory, you're actually assigning that. Then you use data move instructions, LD or SD, so load or store, for the control of information and also for data transfer. All right, let's look at transfer timing. I/O events generally happen much slower than CPU cycles. So it's not like one I/O event corresponds to one CPU cycle. This is synchronous. Data is supplied at a fixed, predictable rate. So the CPU reads, writes every X number of cycles. So it's synchronous. There's a ratio that is maintained. An asynchronous is when the data rate is less predictable, which means the CPU must synchronize with the device so it doesn't miss the data or write it too quickly. And so that's the big difference between those two terms there. Going on with transfer control. This is when you ask who determines when the next data transfer occurs. So how do you know when one is stops and the next one begins? The easier way to do this is through polling. The CPU keeps checking the status registers until new data arrives or the device ready for the next data. So it's pretty much asking, are there yet? Are there yet? Are there yet? It's a constant question ask of, am I receiving new data? Is there new data? Is there new data? It's constant. The other thing that you can do is interrupts. And with an interrupt, the device will send a special signal to the CPU when new data arrives or the device is ready for the next set of data. The advantage of this over polling is that the CPU is freed up to perform other tasks instead of constantly pulling the device. So it takes the burden off the CPU. Instead, it's the device itself that is doing that. All right, and so this is, this line kind of describes it. The CPU is thinking more like, wake me up when we get there, rather than kind of having to constantly ask if the data is there. It's just, when the data arrives, let me know, then we'll handle it. All right, with the LC3, we have a couple different I/O registers here, and you can see here's some sample ones. And so here in this first one, it says bit 15 is one when the keyboard received a new character. With the second one here for the keyboard data register, bits 7 to 0 contain the last character typed on the keyboard. And with the display status register, bit 15 is 1 when the device ready to display another character on the screen. And with the display data register, the character written to bits, which is 7 to 0, will be displayed on the screen. Remember that those numbers correspond to, if you took your instruction line and put it out into the 15 bits for that opcode, we typically look at all those different things. 15 is corresponding to line 15, and 7 to 0 is, of course, the last 8 digits in that instruction. And of course, this is your memory mapped I/O. All right, and asynchronous devices are synchronized through status registers. So these status registers are what you'll encounter when you have to deal with asynchronous devices. All right, with polling and interrupts. All right, let's look at with things for input from the keyboard. When a character is typed, its ASCII code is placed in bits, ranging from 7 to 0, of KBDR bits. Remember, 15 to 8 are always 0. The ready bit is then set to 1, and the keyboard is disabled. Any other type characters will be ignored. So when the KBDR is read, KBSR is then set to 0, and the keyboard is enabled. So that's how it's able to say, hey, I'm ready for the next character to be typed in, rather than waiting for the next string. Of course, here's a visual representation. So you have a KBDR. Remember, these first set of 8 bits here are, of course, the 0 ones that we were talking about up here. And then this right here is the keyboard data. So whatever character that you typed goes right here. And then the KBSR is what toggles the mode for enabling or disabling the keyboard. So here's a basic input routine. All right. So this is using, you can see here, it's using a poll method, not an interrupt. So it's polling, it says load, and we're loading from register 0, KBSR, TR. And here we have a branch, 0 and positive, and we're going to poll, load, register 0 again. And you have DR operation. And it's going to keep doing that, so just pretty much polling for more and more characters. And as you notice, it'll say in here, we're filling with these 2 commands that we saw from the previous page. So this visual diagram kind of makes a little more sense than just looking at the code necessarily. So what happens is that first, when you have your polling operation intact, it asks if there's a new character typed. Right? If not, it loops back around until pretty much you have typed a new character. If there has a new character been typed, then it goes ahead and reads the character and processes it accordingly. All right, here's a quick simple implementation. This is memory mapped input. And in here, the big thing to take away from this visual diagram here is that the address control logic determines whether MDR is loaded from memory or whether it's loaded from the KBSR, KBDR registers. So that, of course, is corresponding to right here. All right, now we've done a lot of discussion with input. Let's talk about output. So outputting to the monitor. When the monitor is ready to display another character, the ready bit, DSR15, is set to 1. When the data is written to the display data register, DSR15 is set to 0, and the character in DDR 7 to 0 is then displayed. So remember, before we had 7 to 0 store, when we first typed it in, that character, again, 7 to 0 is the character display. Any other character written to DDR is ignored, while DDR15 is 0. And again, here's our 2 pieces. Here's DDR. Output data is right here. And this is your ready bit, which is either 0 or 1. And of course, here's the basic output routine. So this is now taking that information, similarly like we saw before. And you can see now it's doing a pull operation, and it's going to load from register 1, and then it's going to store that in register 0. So let's go ahead and interpret this here with a visual diagram. So it's going to ask if the screen is ready to receive information. If it's not, it's going to keep asking whether or not it's ready to receive new information. Once it is ready, then it's going to go ahead and write out whatever character is what was stored in memory. Now, here's a keyboard echo routine. Usually your input character, so whatever the person types, is also printed to the screen. The user in turn gets feedback on character type and knows it's okay to type the next character. So in here you have a polling operation and a second polling operation. This is loading it, and this is printing that character back out. And so what it does is that it is asked if there's a new character. If not, it goes back and keeps asking for a new one. Otherwise, if you have yes, it reads that character. Then it goes ahead and asks if the screen is ready. If not, it just keeps asking if the screen is ready. Otherwise, once it is, it writes a character. So this right here would be pretty much like a complete input-output polling program right here. You have other code that you could put in here, but this would do a basic thing of reading and writing your code. Now, that was poll-based, but let's look at interrupt-based, because remember, interrupt is less taxing on the CPU. So an external device can force currently executing program to stop, and it can also have the processor satisfy the device's needs. Another advantage of interrupt-driven is that it also can resume the stop program as if nothing has happened. So it's really just kind of like a state suspension, rather than ending it and having to start all the way back over it from the stop. It's more like you just paused it, and then you're pressing play and it's resuming where you left off. So why the need for interrupt-driven I/O? As we've kind of mentioned, polling consumes a lot of cycles, especially for rare events. These cycles could instead be used for other things, such as more computation, using things for arithmetic operations and stuff like that. So, for example, the process previous input while collecting current input. So, if you wanted to take that previous input and you wanted to have it do maybe an addition operation, or you're having it do some kind of multiplication operation, you can do that while collecting the next input. Right? That's one of the advantages of interrupt-driven I/O. And here's our interrupt-driven I/O diagram here. So to implement an interrupt mechanism, we need a way for the I/O device to signal to the CPU that an interesting event has occurred, such as a keyboard stroke. A way for the CPU to test whether the interrupt signal is set and whether its priority is higher than the current program. This is done through generating a signal. The software sets interrupt enable bit in the device register. When the ready bit is set and IE bit is set, interrupt is signaled. So in here, if you look at this diagram, this is our KBSR that we saw before. Remember before, when we saw this, we only had this ready bit available to us. Now when we look at interrupt-driven I/O, we're looking here also at bit 14. All right, so if this bit is enabled, then that means interrupts are going to be used. All right, let's talk about priority. Every instruction executes at a stated level of urgency. So for the LC3, the priority levels are PL0 through PL7. For example, the payroll program runs at PL0. A nuclear power correction program runs at PL6. It's okay for a PL device to interrupt the PL0 program, but not the other way around. So in other words, what that means is that the higher that number is, the greater that priority, and the lower number, the less the priority, and the lower priority program should not ever have to interrupt the high priority program. Priority encoder selects the highest priority device, compares to current processor priority level, and generates an interrupt signal if appropriate. Testing for interrupt signal. In this case, the CPU looks at the signal between the store and the fetch phases. If it's not set, it continues then with the next instruction. Now, if it is set, it transfers control to the interrupt service routine. All right, so remember, this is looking back at if the interrupt signal is turned on. So if it is not turned on, it just proceeds on with the next instruction. So it just goes through the fetch routine here. If it is turned on, we transfer that over to the interrupt service routine, which then is going to proceed to check for those interrupts. And that concludes our notes, folks. Until next time.